Welcome everyone to this video where we're going to talk about activities of ionic solutions. Right? So no surprise in ionic solutions, ions interact, right? You have a bunch of positive charges and negative charges all floating around in a polar solvent and things like that, right? You got a lot of electrostatic interactions, okay? And often for high concentrations of ions, which really molalities greater than 10 to the minus 4 can be considered this, okay? One really should be using activities instead of concentrations of those ions in solution, okay? Right, where the activity is that effective concentration, okay? When dealing with like equilibrium problems or other things of that nature, right? And recall, right, for solutions, right, for that solute, that activity is related with the activity coefficient times the molality, right, divided by 1 molal, right, just to make that a unitless quantity, okay? Well, for an ion, right, if I dissolve some ion, right, let's consider just the cation with an anion, right? So I dissolve this in solution, right? I get some number of cations in solution, some number of anions in solution, okay, right? That gives energy, right, is going to be related with the amount of cation in its chemical potential plus the amount of anion in its chemical potential, okay? Right, and for some sort of real solution, right, we're going to get the ideal gives energy plus then, right, some correction due to the activity coefficient, right? If we recall when we talk about activities, right, that chemical potential is related with the standard chemical potential or the pure, right, plus RT ln of the mole fraction, right, which this is your ideal case, and then you had on top of that RT ln of gamma, right, which is your right, all of your non-ideal behavior, okay? So that's kind of what we have here, right? And so the Gibbs free energy, right, for some solution that contains ions in that solution, right, is related with the ideal Gibbs energy plus then this correction here, RT ln gamma, the cation and the anion gamma, okay? Those activity coefficients for the cation and the anion, right? What we're going to define is the mean activity coefficient, which is going to be the P plus Q root of the product of the cation and anion activity coefficient, okay? And so, right, given that, right, then the activity of some ion is related with gamma plus or minus that mean activity coefficient times the molality of that ion, right, which is what is used here, for example, right, in this Ka expression for a weak acid, okay? And again, so we're going to replace the activity for the cation, the activity coefficient for the anion with this mean activity coefficient. So we're going to take kind of the average of those activity coefficients for the anion and cation, okay, and then apply that same activity coefficient for both things. This is an approximation, but we can do this, okay? And that means that this non-ideal behavior, right, is effectively assigned equally over both ions, okay? Right, that the chemical potential of the cation, right, and the anion have that same correction from non-ideal behavior, right? And how can we get this mean activity coefficient? Well, we will use the Debye-Hückel limiting law, okay? So it was derived and shown that this mean activity coefficient is related with this equation, that the log of your mean activity coefficient is equal to negative times the charges of your ions times A, which is just a constant, times I, the ionic strength of the solution, to the 1/2 power. And we'll explain what some of those are in the next slide or two, right? A here is literally just a bunch of different constants, right? And you do not need to know that, memorize that whatsoever, okay? You'll just be given a value for A, right? For aqueous solutions, right? So solvent water, right, at 25 degrees Celsius, A is 0.509, right? And that's basically what we're just going to use, right? Is A is 0.509, right? If otherwise, you could potentially calculate it given the properties of your solvent and things like that and your temperature, or you just look it up somewhere. What is the that constant A for a given solvent at a given temperature? Okay. Right, so that is what A is, and then the last term is I, what is called the ionic strength of your solution. The ionic strength of your solution is the sum of the charges of the ion squared times the molality of that ion, right, divided by 1 molal to make it a unitless quantity, right? So for example, if I just have 2 ions in solution, right, it's going to be 1/2 times, right, the sum of the charge of the cation squared plus the concentration of the cation plus sum of the charge of the anion squared times concentration of the anion, right? And all that's divided by 1 molal, right? B naught is just 1 molal. It's just there to make things unitless, basically. Okay. And so, right, here is kind of right. So this ionic strength can basically be written in terms of some constant K times B, where B is the concentration of the undissolved compound, right? So the concentration of like sodium chloride or calcium nitrate or something like that, right? The concentration of the salt of the solid, right? Before it dissolves, okay? And then K is just some number, right? So if I have sodium chloride, right, K is going to be 1, right? Because for sodium chloride, this is 1, this is 1. B plus and B minus are equal, and there's equal to B, right, which is the concentration of sodium chloride. And so I get 2 times B times 1/2 gives me just B, right? So that's where that 1 comes from, right? So that's where all these different numbers come from, 1, 3, 6, 15, blah, 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 just from these different combinations of charges of your cation and anion, and what, for a 2-ion solution, right, what this simplifies down to, right, assuming those charges, those ions are coming from the same salt. Okay. Now, if we want to go beyond the Debye-Hückel equation, okay, all right, go to the Debye-Hückel limiting law, right, where we see, okay, so what's plotted here is I'm plotting 100 times the square root of the ionic strength versus log of gamma, right? This plot, assuming it behaves the Debye-Hückel equation, right, should be a straight line, right? Because the log of gamma is equal to some stuff times ionic strength to the 1/2 power. Okay, so this should be a straight line, and that is what we see for low ionic strength solutions, right? And even for high ionic strength solutions where you have just, you know, a equal charge as your cation and anion, right? But for some systems, right, for example, this magnesium sulfate, right, here you have 2 plus 2 charges, so the strength of the charge of your cation and anion are greater, right? And you see that for the same ionic strength, you get much greater deviation, right? So the dashed lines are the ideal values, right? And the solid lines are the non-ideal values. And so you get much greater deviation from ideal high ionic strengths, especially when your anions and cations have high charges, okay? And if you want to try to correct for this, you can, again, then go to this extended Debye-Hückel equation, okay, which is related with the limiting Debye-Hückel equation, kind of given up here, right? And then you have some extra terms that are dependent upon the ionic strength, and then B and C, which are just some sort of constants that are determined empirically, right, by fitting to this equation with data that you obtain in lab, okay? And so that is how we get the activities for ionic solutions, right? So when we talked about gases and general mixtures of two liquids and things like that, the activities we had to find experimentally and things like that using vapor pressures and mole fractions and other things like that, right? For ionic solutions, given the concentration of the ions, we can estimate using the Debye-Hückel limiting law what that mean activity coefficient is, and thus then the activity of those ions in solution.